This afternoon or morning, whatever it is, I guess it's morning, I'm going to talk about heat acclimation, physiological mechanisms, and its impact on aerobic performance. The outline that I'm going to talk is that I'll first examine what is heat acclimation and its actions. We'll get into the physiology because the physiology is very interesting. We've had a lot of discussions yesterday what limits aerobic performance, and we all got different opinions and we've got a lot of commonality. But when you look at adaptation, the body pretty much knows what limits performance, so when you look at the adaptations, that actually might give you insight into mechanisms. And then we're going to go from basically acclimation to acquired thermal tolerance, which are some of the cellular adaptations. So if we say heat acclimation, what is it induced by? Over years, we've learned that it's due to repeated exposures over many days, that you need heat stress sufficient to increase body temperature, but very importantly, to induce profuse sweating. Core temperature alone is not enough. That the duration, optimal duration is about 100 minutes a day, that it takes 4 to 14 exposures of days, that the more fit you are, the quicker you acclimate. And just like specificity of training, there's specificity of heat acclimatization. If you're exercising, you're going to acclimatize a little different than if you're resting. So it's very intensity, duration, as well as the type of heat stress, whether it's tropic or desert dependent. The three primary actions of heat acclimatization that I'll discuss today are thermal comfort, physiological strain, and aerobic performance. In each little section, I kind of give you the summary of what I'm going to tell you, and then I've just picked a few selected slides. So if you get repeated exposures to the heat, one of the first things you notice is that on the fifth day, you're much more comfortable than the first. And this was one of the few slides that I could find that I thought really showed it nice. What we have here is a psychometric chart with dry bulb temperature, the amount of water in the air, and then you have your relative humidity lines. And you can see that if you look at basically what's comfortable for unacclimatized people, that after undergoing a heat acclimatization, that this moves up and that they're more comfortable in higher humidities and higher ambient temperatures. So the first thing then is more comfort. The second is reduced physiological strain. And I've got a lot of older studies because these facts have been known for many years, and I've tried to find some of the original studies that basically I think did a nice job showing it. So here's a study by Sid Robinson back in the 40s where they looked with heart rate over repeat and core temperature and skin temperature over up to 24 days of heat acclimatization. So each day they exercised in the heat and they plotted their responses. What you can see from the first day to basically it plateaus maybe after 8 or 12 days, you can see large reductions in heart rate to do the same exercise task, large reductions in core temperature, and in this instance, a very large reduction in skin temperature. So the physiological strain of that task is reduced markedly. If we look at physiological strain, it's important to note that heat acclimatization is not the same as physical training. And Carl Gasolfi did a nice study where they got a bunch of individuals pre-training, they had them exercise in the heat, they measured the core temperature and the heart rate. They then had them go back and exercise in the heat after 11 weeks of physical training, intense physical training. And then those trained individuals then underwent a heat acclimatization day, which was much lower intensity work than their training, and again, a very short duration. And what you can see that when they were unacclimatized and untrained, here's their responses, and they didn't go very long in the heat. You can see high heart rate, high core temperature. That after 11 weeks of training, they picked up a little bit of acclimatization because their core temperature and heart rates were lower. But then if they actually went in the heat, you can see very large reductions in core temperature and heart rate. So it's not the same as physical training. It's an independent process. But we do know, and I didn't have the time to put in the slide for the shortness of the talk, is that fit people will acclimatize quicker. So we know then that also that, and it's been discussed, that if you are acclimatized, that you can improve your ability to do aerobic work in the heat. And here's, I think, a very nice slide taken from a study by Dr. Nielsen, where what they did is they had the individuals heat acclimatize, and each day, this is just a representative subject here, that they basically had them do an exercise task in the heat after repeated days in this 40-degree environment. And you can see this very nicely shows that on the first day, here's a person, here's their esophageal temperature. They don't go very long and they get a high esophageal temperature. The next day their esophageal temperature is a little lower at each point in time, they go a little longer, and each day that they can continue. So that if we looked at the group after 10 days of heat acclimatization, at least with this exercise task, they improved their ability to work by 70%. And at each day, and I think this is a function of the experiments, they ended up basically discontinuing at about the same core and the same mean skin temperature. So they kind of worked up to the same point. Now, a recent study has suggested is that not only does heat acclimatization improve your ability to work in the heat, but it's possible perhaps that it may improve your ability to also work in a temperate environment. And here's a study again by Santiago Lorenzo, where they had individuals do a time trial performance, unacclimatized. They then had them undergo 10 days of heat acclimatization in a 49-degree environment. Again, low intensity, so there's not much training. Here's your line of no difference. And you can see that if you look at the hot environment, everybody showed improvement, as well as in the cool environment, those that were tested in the cool environment. So that heat acclimatization improved time trial performance, and in this instance by about 6-7% in temperate and a hot environment. The same study suggested that heat acclimatization might be able to improve VO2 max. Again, you can see the same thing, the line of no difference in subjects that were tested in both a hot and a cool environment showed specific to that environment improved VO2 max after acclimatization. This is new data. If you go back, heat acclimatization studies haven't historically done a lot of performance tests, but there are suggestions in the literature. But most of the studies that have suggested it have not done control groups, and these studies did. So that may or may not be true, but there's a suggestion. So if we look then at the physiology of heat acclimatization, we have the two outcomes, reduced strain and improved performance. You can see I have on this table a whole host of physiological adaptations that occur. What I'm going to do is I'm going to go through some selected of these and basically show you what some of the data will show. Probably, at least in my opinion, one of the most important adaptations is an improved sweating response. What you find is that the sweat rate turns on earlier. Once it turns on, there's a greater increase in sweating for a given change in body temperature. Your maximum sweat capacity goes up. That if you're in a tropic environment and you're unacclimatized, what you'll find is that you'll get a suppression of sweating from wetted skin after a while. That goes away. And that the distribution of sweat over the body so that you can maintain total skin wettedness is improved. Here's a classic study done by Dr. Ethan Nadell, which is, again, you see these kinds of slides when you do thermal regulation because you're looking at a physiological effector response. Here it's chest sweating as a function of the drive for sweating. Here it's esophageal, but it's either esophageal or some weighted. But what you can see, most importantly, is that if we have an individual before training in physical acclimatization, the sweat rate turns on and it increases in a linear manner. Dr. Nadell then had the individuals undergo a physical training study, and you can see that this improved the sweat response somewhat. Maybe it didn't turn on earlier, but there was a little bit better sensitivity. And that if you acclimatize, what happens is your sweating rate turns on at a lower internal body temperature and increases faster. So you get that evaporative cooling earlier, as Dr. J showed that you then have less heat storage and you can better sustain your temperature responses. These data have been repeated many times by others. So we think that it turns on earlier due to the central nervous systems and adaptations in the central nervous system so that the heat loss signal comes down at a lower internal temperature. But also, as we showed, that the sweat glands will start producing more. And it had been known for a number of years ago that at least it was thought that in animal models that what happens is with acclimatization there's more acetylcholine released to the sweat glands, and the sweat glands are sensitive to acetylcholine. So it thought that that improvement was due to increased acetylcholine release. But again, a recent study out of Chris Minson's lab looked at sweat rate, and then they did microdialysis to infuse acetylcholine to the sweat glands, different dosages, before and after acclimatization, and again a control group. And what you can see is that probably get a receptor turning up, the receptors turning up, increased number of receptors at the sweat gland, because you can see, again, peripherally, that the sweat gland for given acetylcholine release is going to get more sweating. So as we've learned, it's not only sweating, but it's also dry heat exchange. And with dry heat exchange, you see some parallels with sweating, that you get the onset of skin vasodilation earlier. Your maximum skin blood flow that you can achieve is higher. The sensitivity of that skin blood flow's response is better. But you also have other factors going on, which I'm not going to spend a lot of time, that we're aware of, but folks don't often understand that this really helps dry heat exchange. One is with the dropping of skin temperature, you lower that core to skin temperature gradient so that you can remove more heat. And secondly, something that I didn't fully appreciate until maybe maybe a year ago, time flies when you get my age, is that when your plasma volume expands, we often think about that filling up the vascular space. But what happens is even with the small changes in plasma expansion, that as you lower that hematocrit, you increase the plasma portion, and you increase the specific heat of the blood. And that actually can count for also a few more percent of what you can transfer heat that can be transferred for a given blood flow. So here we look at the forearm blood flow response, and this is Mike Roberts, again with the Ethan Nadell group, where they again looked at forearm blood flow and esophageal temperature. Different study, but the same paradigm. Here's unacclimatized person, skin blood flow dilates, goes up linearly, doing venous occlusion. Training really didn't do much, and then if you look at the skin blood flow response after heat acclimatization, shown over here, turns on earlier, and the skin blood flow response increases more. So you improve your heat loss responses. Well, you heard us argue the other day that the cardiovascular system stress, so it makes sense that a lot of changes occur within a cardiovascular system. You find that blood pressure is better defended. Heart rate's reduced, as we said. You increase your stroke volume. Your cardiac reserve's increased. That also, studies are emerging that show that cardiac efficiency is improved. And this seems to be related to change in some of the isoenzymes, where you get a transition from myosin from fast to slow isoenzymes. And also the animals models are showing increased compliance of the ventricle. So again, some of the data, I think this is a great one for blood pressure regulation. Again, from the 40s, they had people go out, they had them exercise, carrying a load, to doing hard work, sustained work in the desert, and you look at the number of cases of syncope. And you can see here that I think they had about 40 subjects, I can't remember, but about half of them had syncope the first couple of days, but afterwards they could do the task, they could sustain blood pressure. Here you show, again, the cardiac reserve from Dr. Nielsen's lab. Here's basically before acclimatization at a given work rate, 10 and 40 minutes, and you can see after acclimatization, the ability to achieve higher cardiac outputs during that submaximal tasks, as well as the higher stroke volumes. So again, increasing cardiac reserve. And here's a very nice slide showing the improved myocardial efficiency. And I don't know why this turned out in blue, but again, from Mikhail Horowitz's, some of her nice work, with animals that have been acclimatized for a month, oxygen consumption, myocardial oxygen consumption as a function of rate pressure product. And you can see the reduced myocardial oxygen uptake of the heart doing a given task. Fluid balance is important. We said dehydration's bad. Well, so then you'd expect that fluid balance would be improved. You find improved thirst, increases in total body water, loss of electrolytes are reduced, plasma volume expands, but you find no change in erythrocyte volume. Although the studies that have looked at erythrocyte volume expansion show that it can have a huge impact on thermoregulation, that is not a normal adaptation. So here's a great study by Eichner. They had individuals, they had them basically in a temperate environment and acclimatized for 6 days in the hot wet. They then had them basically drinking ad libitum, and you can see that when they were in a temperate, they were in a cool environment, with the standardized bout, they had a little bit of a fluid deficit of about over a liter that they had due to voluntary dehydration. The first day in the heat, their sweat rates were up, the level of voluntary dehydration was very low, but each subsequent days it reduced, and it ended up being more than halving. So you better match then thirst to water needs. And this is probably due to, well, we can talk in the break what it's due to, but probably due to the electrolytes returning the sodium driving up thirst. If we look at total body water, there's been a number of studies, but very nice study out of Nigel Taylor's lab. If we look here at total body water, you can see it goes up just a little bit. And that if you look at it, it's predominantly in the extracellular fluid volume. These are days 1, 8, and 22, so pre-acclimatization, 8 days and 22. And that you can see the plasma volume goes up, and red cell volume didn't much. Again, most studies don't show much of an effect on EPO or red cell volume. But again, it's very important for thermoregulation. What's been known, though, for many years is that if you are acclimatized, your sweat's less salty. So here's a nice study by Allen where you look at sweat rate and sodium concentration, and you can see regardless of whether you're acclimatized over here or not, the higher your sweat rate, the higher your sodium losses. But then, again, as you can see, here's unacclimatized and acclimatized. So again, the importance of that loss of reduction of sodium in the sweat is that, remember yesterday we explained it leaves solute behind, so that solute goes up in the extracellular fluid, so it can pull from the intracellular fluid to provide a reservoir to support the cardiovascular system and the plasma volume. So total body water goes up, and as a result of losing less sodium in the sweat, you can draw fluids in and you have a greater reservoir to sustain your plasma volume. Now, in addition to this, plasma volume will go up. And this has been something that's been studied quite a bit. And I want to mention that the slides I'm going to show you is because they're from a really classic study done by Charlie Sinet. But they were done in hot-wet. And you probably get a greater plasma volume expansion in a hot-wet environment than you do in a hot-dry. Because in a hot-wet, again, things make sense, more dependent on skin blood flow, so that vascular space gets bigger, so you have a bigger adaptation. So here's basically days of heat acclimatization, the change in plasma volume. And you can see in this study, these are very large increases, up to 20%. And that what Dr. Sinet showed very nicely, and has been done by many others, is that one of the real reasons for the increase in plasma volume is that you increase your total circulating proteins. When you increase your total circulating proteins, it exerts a pressure within the vascular space, an oncotic pressure it's called, so that you can preferentially move fluids from the interstitial to the intravascular space. So that increase in total circulating protein is important. And you can find studies with heat acclimatization that don't show a change in vascular space, but basically you account for stuff, and it's a pretty consistent response, but not as large. With heat acclimatization, and we talk about performance and high-intensity work, there's a variety of metabolic adaptations. One of them that I didn't show is that most studies, not most, but more than half of the studies will consistently show that with heat acclimatization, your energy cost to perform an exercise task is reduced. And I haven't seen that with training or anything else, but you'll find that at least half of the studies will show that your metabolic rate is slightly lowered. So if that's true, that means then you have less metabolic heat to be dissipated. You find then changes in muscle and blood lactate and glycogen. Here's a nice study from Andy Young, where what he did is we heat acclimatized individuals, and here's the muscle and plasma lactate levels. So here's a cool environment. Here's your resting values for, this is muscle lactate and plasma, and then the post-exercise. And what you can see is that with here's acclimatization, increases your muscle lactate, with acute heat stress, and then with acclimatization, basically it reduces your muscle lactate both when exercising in a cool and hot environment, and the same with the plasma lactate. So it reduces then basically your production of muscle and plasma lactate. Likewise, a study done by John Kerwin shows that muscle glycogen utilization, and Andy's done some of this also, but is that your glycogen utilization is decreased with heat acclimatization. And this makes sense probably for a given bout, lower muscle temperatures, lower epinephrine levels, so less muscle glycogen use. So we've really focused on heat acclimatization and basically reducing physiological strain in the mechanisms. But one of the changes that occurs with heat acclimatization is for a given level of physiological strain, you're less likely to have injury to organs or injury or heat stroke. And these adaptations occur cellular, and they're called acquired thermal tolerance. And acquired thermal tolerance, again, are cellular adaptations caused by a single or severe non-lethal heat stress that protect the cells from heat exercise and other stresses. And Mikhail Horowitz has shown that if you induce heat acclimatization, that there's a variety of other stresses that they're protected from. And again, it causes that, and I'm over time. But all I want to say is that one of the adaptations that occur are called heat shock proteins. And here we can look at different tissues. The amount of increase in these proteins basically are dependent on whether you have physical exercise or heat. And you can see here's soleus and left ventricle. And that exercise can cause heat shock protein responses, but if you have heat stress, they're even greater. That if you acclimatize, here's a study we did, we acclimatized individuals, and here's 2 heat shock proteins, they go up. Here's HSP 72s and 90s, so your constitutive levels increase, and that the increase in 72 is related to basically the increase in heat shock protein 90. So in conclusion, since my time's up, I'll say that acclimation reduces strain and improves performance. It's specific to the type of heat strain. Improvement in evaporative cooling is critical to acclimatization. That there's cardiovascular, fluid, and metabolic adaptations that are important for heat acclimatization. And there's also cellular adaptations that allow the tissue to be more protected. Thank you.
Thank you for a very nice presentation. I think you could have gone on for a very long time on this topic.
Yeah, I mean, it's like covering physical training in 20 minutes.
Okay, are there questions?
Thanks, Mike. Great talk again. Thank you. Got a couple of questions, actually. The first one is about the idea of specific heat changing with acclimation. That's a really interesting idea. So the specific heat of the blood is going to change with the fluid shifts?
Right, because basically the specific heat of the water is higher than the solid content.
And total body water changes as well.
Total body water will go up, so the specific heat of the body, if that's what you're getting at, theoretically will also go up.
Yeah.
Getting back to your heat storage calculation.
Yeah, it's a really cool idea. I like that.
Another paper for you.
Thanks. I'll put you in the acknowledgements. Another quick question is, in terms of the physiological control of both skin blood flow and sweating, I don't know if you can answer this together. We see the changes in the onset thresholds for both those effector responses with heat acclimatization. How does that, do we still see the same thing if we express the forcing function as a change in esophageal temperature from rest, or is it really merely a function of that lower absolute esophageal temperature following acclimatization?
I don't know the answer to that. Oh. My guess is that, at least for sweating, either way you're going to see it. The change in the threshold for skin blood flow is not quite as great, and that may or may not be. But you see a big drop in threshold temperature. And we don't consistently see drops in resting core temperature. Some people do, you know. So maybe they're more careful than us.
Thanks very much.
Hi, Mike. Excellent presentation. I've got about 15 questions, but I'll keep it to one. You've talked about acclimation and acclimatization. And acclimation, well, most of the studies are done in the lab with acclimation. Yeah. Is there a difference, or has someone looked at different adaptations related to acclimation and acclimatization? Yeah, that's a good question. Acclimation is basically done in the lab, acclimatization is done outside. And if I had more time, I would have put that slide in. But the responses are the same. But when you have true acclimatization, and as Mikhail Horowitz has shown, she'll break it down to short-term and long-term acclimatization. And we really study. So with true acclimatization, there's probably more long-term adaptations than we study in the lab with acclimation. Okay? I'll just leave it at that. But it's the same. You know, stress is a stress. You make it up in the laboratory or whatever. Oh, okay. Interesting, though, for cycling, for example, if you cycle in the lab, you wouldn't have a convective flow, whereas in... Well, again, and this is something we get into, you ask about, acclimatization's really been
put together for military, occupational, and stuff. So how do you apply acclimatization to an athlete? I mean, it's really a new area, and if you take some of the ideas of training, I think there are some ways that you might be able to do it. But it gets back to the earlier point I made, is that just like specificity of training, there's probably specificity of acclimatization. So if I could go outside and ride a course in the heat, I'm going to get the different types of intensities, and the different pulses are going to have different, basically, upregulation of genes, and my adaptations will occur. So,
I have one question
I
regarding,
We're,
if I have time.
can you make it quick?
Yeah, just a quick
Please.
question.
Thank you.
It is regarding for a team A who's coming from 10 degrees Celsius, usual temperature, and a team B coming from 20 degrees. How much time does the duration to acclimatize changes?
well, there's two parts to that question. One was brought up yesterday. So the first part is directly related to your question, and the other part I'll bring up. I'll pretend that you asked it too. How long it takes you to acclimatize is really going to be dependent on how unacclimatized you were. It's not necessarily from the environment that you came from. Okay, so that's why fitness gives you a little bit of an advantage. But when you talk about adaptation, and we study heat, cold, and altitude, and whether it's physical training, all the time courses for adaptation are about the same. And this has to do with basically the molecular machinery of turning things on and adjusting. And that a lot happens in 1 week, quite a bit happens more in 2 weeks, and by 3 weeks you're done. Okay? So generally, if you've had some heat acclimatization, you can do a lot the first couple of days. Second is, I'll go back, is yesterday there was a discussion about cold acclimatization and would it interfere with heat acclimatization. Two completely different processes. The colds, most people don't really acclimatize to the cold, and they're very subtle. It's more of a called habituation, where your body learns to ignore the cold. And I don't see any interference with that, at least, from my limited knowledge of those two mechanisms.
Okay, thank you very much, Mike.